Move to another concept which is subgroups. So before that we need to define some more terminologies. So first one is order of a group, okay, calls group G. So this is nothing but the number of elements in a group, right? So let's define the number of elements of a group is called its order. Okay, so we will use either this or order of G to denote order of G. So let's see an example. So if you look at our previous example, integers and addition, here the order is infinite because there are infinitely many elements here. Now if you look at some group U10, the group of units, you can see that it is 1 3 7 9. So all those elements which are GCD is 1 when compared with 10. So here the order of uh, group, order of U of 10, you can see it's only 4 elements. Okay, so in this case we call it as a finite order. Okay, that's about group orders. Now, okay, similarly for any Zn, the order of the group is equal to n because 0 to n minus 1. So let's look another definition. Order of an element, order of an element of group. So initially we thought, right, we talked about order of a group, that is the size of the group. Here now we are looking at order of an element of a group. So this is a little different. So let's see what this means. The order of an element G in a group G is the smallest positive integer n such that whatever the operation, if you do operation like this up to n times, you will get the identity n times. So we will rewrite the same thing as a notation G times up to G equal to E, or we can write G raised to n is equal to. So it is understood that the star is an operation, right? So if you are in adding things, then this must be, operation would be like that. So n times. So then this will be translated to n times G is equal to E. So depends on the operation. So main idea is if you operate n times G with itself, you should get back E, right? So the first time such n is happening, that n is your order of the element. So we denote this by n is equal to order of G, or similarly modulus of G. Okay, that is the idea. So let's see some. So how to find order of an element in group? So to find order of G for G belongs to G, what you want to do is you try to calculate the sequence G, G square, g cube like that. At some position you get g raised to n equal to e for the first time. So this n is your order of g. Okay. So let's see one example. So let's take the group U15. So what is U15? So these are all k such that k is between 1 and 15. Also GCD of k and 15 is equal to 1. So this is a group. So this is defined as multiplication modulo n. That is, two elements are multiplication modulo n means normal multiplication and take the remainder when divided by n. So here it is 15. Okay, so let's see what is the order of 8. What is the order of 8? So start writing the sequence 8. So 8 is 8 in mode 5, mode 15, right? Now if you do 8 square, you get 64. 64 mode 5 15 it will be, how many times in go? It is 4 times you will go 15, then what you get back is 4. So what you want? You need to get an n such that 8 raised to n is equal to, the identity here is 1. So what is this n? That is a question. So 8 square is 4. Now 8 cube is, you can write it 8 square into 8. So 8 square is already 4, so you can write 4 into 8. So now it is 32. Now what is 32 mode 15? So 2 times will go, so rest is 2. So 8 raised to 3 is 2. Now find 8 raised to 4. It is written as 8 raised to 3 times 8. 8 raised to 3 is 2. 2 times 8. So 16. Now 16 mod 15 is equal to 1. So what happened is 8 raised to 4 is 1 in U15. That means you got the identity. That means 4 is the order of 8. Okay, so this is the method. So depends on the operation, the idea will change. So let's see one more example in additive group. So let's see order of 3 in Z7 under addition modulo 7, right? So let's see how it is done. So first you calculate 3. So 3 is 3 mod 7 is 3 only. So to understand what you want to find out, so you need 3 raised to n has to be the identity of the group, that is 0. What do you mean by 3 raised to n? You are adding 3 plus up to n times, right? Should be 0, or what we can write is, how many times n is there? N times 3 has to be 0. This is your idea. And so not simply n times 3, mod 7 has to be 0. So you should find such an n. So that is the order. So 3 will not work. So 3 square means what? So 3 raised to n is n into 3. That means it is 6. 2 times 3, which is 6 mod 7. 6 mod 7 is 1, right? No, 6 mod 7 is 6 itself, right? So now the 12 mod 3 power 3 we will try. So 3 power 3 is 3 square times 3, right? So this 6 times 3. So 18 mod 7. So 18 mod 7 is 4 only. Okay. Now yeah, I should do something. So the meaning is not multiplication. So you have to multiply 3 into 3. So it is 9 mod 7. It has to be 2. Okay, because 3 raised to n is equal to n into 3 in case of additive groups. Now 3 raised to 4 is 4 into 3. This is 12. 12 mod 7 is equal to what? It is 5, right? So still it is not 0. Let's do 3 raised to 5. It is 5 times 3. This is 15 mod 7. So that will be 2 times it will go, it will 1. So don't be stop here. This is 1 is not the identity of in additive group Z7 plus 7. So you need to get 0. Now theory to 6 we will see 6 times 3. So it is 18 mod 7. So what you get is 4. Okay. Now you can work out 3 power 7. So 7 times 3, this is 21 mod 7. So 21 mod 7 is 0. Why? Because 3 into 7 is 21. So completely 7 divides 21. So what you get is 3 raised to 7 equal to 0, or you can write 7 times 3 equal to 0. That means 7 is the order of 3 in the group Z7 plus 7. Okay, so this is the way you have to find the order, right? So that's the idea. Now let's come to what do you mean by a subgroup. Okay, so if a subset H of a group G is itself a group under the same operation, under the operation of G, we say that H is a subgroup of G. Say subgroup of G. So we denote it by H is subgroup of G. So what you need to understand is you have a big set G and you are selecting a small subset of whatever the subset. So what is happening is H is a subgroup. First thing you need to say, the operation on G, if you take any B in H, then you should need AB is in H. So AB is in G because G is a group, but here if H needs to be a subgroup, then AB must be any element AB taken from H, it has to be the product also is there. Second thing is E must be an element of H, that identity should be inside of H. Third thing, for any element H, that A inverse should also belongs to H. Okay, and associativity should be there. So associativity follows from G. So that is need not to check. So checking is whether it is closed, so the operation is closed. Okay, any two elements from H, it again belongs to that H, and his identity is in H, and for every A is A inverse in H. So these all are satisfied, then we call that H is a subgroup of G. So same operation is very important. So right. So let's see one example, like a simple example I will take first. You take the element. So one thing it's very clear that the element, the subset H, so H, if you take H is equal to G itself, it is a group. It is a group. So that is a, it is a that is a subgroup also. So the full set is again a subgroup. Again, if you take H is equal to singleton set E, it is also a subgroup. Also a subgroup. So these sets are not interesting. So now we call the first thing, if H is not equal to G, we call H is a proper subgroup. Proper subgroup. And if H is not equal to this we call H is non-trivial subgroup. So that means this is we call trivial subgroup. Okay, these are the interesting facts. Now let's see some examples. So I'll take one example in a multiplication group, like you take minus 1 1. This is a subset of real numbers, right? So this is a proper subset of R star. That means 0 is removed. Now consider the group R star under multiplication. We know that this is a group because it satisfies all the group axioms. And also H is a subgroup. Now we can see H under multiplication also a group. So that makes H is a subgroup of R star, right? So, and in this fashion you can see many groups like that. We have seen in integer under addition is it is a subgroup of it is a proper subgroup of R under addition. So R under addition is again a subgroup of C under addition, right? And what about multiplication case? A Q star under multiplication is again a proper subgroup of R star under addition, multiplication. Also C star is a subgroup of, yeah. So they are all same operations. That's interesting, right? Now so you take any. So now also look at why when it is, so you can look at Z3, it is 0 1 2, like so 0 1 2 as a set is a subset of integers, but Z3 is not a subgroup of Z under addition, because Z3 is under normal addition, is not a group. So here it is a group, but under multiple addition modulo 3, but that is not the operation under set. So this cannot be a, so operation has to be same, and the subset it has to be a subset also. Okay, so this is very important. So now we have seen that if you take all the subgroups H of G, that intersection, right? If you take all the subgroups, the intersection is non-empty. Why? Because E belongs to H for all H. Now my question is, if I take so let's write so what about the intersection? If we are given, so given H and K are subgroups of G, what about H intersection K? Is it a subgroup? Is it a subgroup? So let's see, it is in fact. So how do you prove it? Okay, so we have to prove the closure property, right? So let's take AB from H intersection K. So this proves that AB is in H and AB is in K, because H and K are subgroups. That means AB is in H and AB is in K. That means what? AB is in H intersection K. So if you took two elements from H intersection K, it is again, so closure property is there. Closure. Second thing is identity is there. Yeah, E is in H and E is in K, so automatically E is in H intersection K. Now for the inverse case, you take A in H intersection K, so this means A inverse in H, also A inverse in K, right? This means what? A inverse is in H intersection K. So it all satisfies. So H intersection K is a subgroup. So H intersection K is a subgroup of G. So this can be extended. If you take any, you take all intersection of all subgroups, then if H is running over all subgroups of G, this intersection set, this is going to be the subgroup of G. So that's what you can show. So once you said something about the intersection, is it true for the union? So the next natural questions is H union K a subgroup. So let's think about it. You just think about whether it is possible or not. So it is very clear that if E is in H and E is in K, then surely E will be in H union K. So identity exists in H union K. That's not a big deal. Now what about closure property? So let's take one counterexample to this. So let's take a group G is Z under addition. Okay, so now let's consider two groups. So let H is all elements of the form 2K where K belongs to Z. So this is going to be a subset of Z, right? And also it is a subgroup under this. So H plus is a subgroup. Why? Because if you add two elements, you get an even number. These are a set of even numbers. Now for the inverse also, if 2 is there, minus 2 is there, so minus 2 is also even, right? So inverse exists, identity exists, everything is there. So this is a subgroup. Similarly, you take K is equal to some 3 times H, where H belongs to Z. So this is also a subset of Z, and similar are given. You can prove that the multiples of 3 also is a subgroup. So we can call these H and R simply like this: H is equal to 2Z and K is equal to 3Z. Okay, what about what do you mean by H union K? So H union K is nothing but it contains all elements of the form H 2K and 3H where H and K are integers, right? Now let's take, so it is very clear that 2 and 3 in H union K, and if you consider operation addition, 2 plus 3 is equal to 5, but 5 is not in H union K. Why? Because H union K contains all multiples of 2 and 3, so there is no summations are there, so 5 is not in that. That means plus is not a binary operation on 3Z union 2Z. That is, H union K is not a group under addition. Okay, so union need not be a group. Okay, so when it is possible, I will give you a hint of this. So if H and K subgroups of G, then H union K is a subgroup of G only when either H is a subset of K or K is a subset of H. Only this case we can prove that H union K is a subgroup. Otherwise it is not. You can verify. You can verify this. So H union K is a subgroup of G only when either H is a subset of K or like this. Either this has to happen or this has to happen. So if this happens means what? H is a subset of K means H union K automatically becomes K, right? But K is already a subgroup, so H union K is a subgroup. Okay, you got the idea, right? So these are the only cases where you can form a unions becomes a subgroup. Okay, keep that in mind, right? Yeah. So now we move to how do we check if you are given. So next question we have to address is given a subset H of G, how do we check H is a subgroup of G? Okay, so is there any simple way? Is there any simple way? Okay, so this we will look at in the next lecture. All right. Thank you.